views on WWVB.
Okay, can you hear me? Microphone is off, but I'm kind of naturally loud as an Israeli, so I guess I don't need it. Oh, I didn't put it on. Thank you. So I want to start by thanking John for giving me the opportunity to work on the improvements of WWVB broadcast. It's been a fascinating R&D project. It's still going on. It's been going on for more than a year. And it has all these entities involved. So we don't have time to go into the bio of each one of them, but it's worth realizing we have this team from NIST led by John and the station team led by Matt. Under John's supervision, we have Peter Henson from the Navy, who's been a key figure to try to look him up and see the publication that he has in this field. And then there's the team from ExtendWave and university collaboration. And it's particularly good to have a PhD candidate that has that as her topic of her PhD dissertation. So at 11 o'clock at night on a Sunday, if I need a plot to be produced slightly differently or a different scenario, I send her an email, and in 20 minutes I get it back. that really works well. Okay, so what we're going to try to cover, and it's a little bit hopeless, we have 21 pages of a paper that you find in the proceedings, covering overview of the WWVB station, what kind of reception challenges we're trying to address with the new system, ranging from modulation changes, encoding, etc., and then all the analysis associated with the performance improvements. So whatever we can get done, and the rest you're going to have to see in the paper. So a little bit of overview for the WWVB broadcast, including some history. It's operated by NIST out of Fort Collins. You're probably familiar with that. It's very popular, and you know, actually coming in on the flight, I noticed on the second page of the magazine of Sky Mall that atomic clocks by Casio are being offered. These are at high cost. The one that I bought is only $40, but it's definitely very popular, and it's growing in popularity ever since the station's power has been increased to like 70 kilowatts. But the modulation scheme and encoding were defined in 1965. Okay, that's when NASA had a little less computing power than I have in my mobile device. They have since caught up, I hope. But the idea was to come up with something very simple that one can decode with like an envelope detector, just like the AM broadcasting, which preceded FM being superior. And so a lot of what I'm going to present is about that, improving the modulation scheme so as to get better performance out of the same amount of power. This is what the modulation looks like. Modulation is all about how you vary the properties of your carrier, a 60 kilohertz carrier in our case, in order for it to carry information. So what is being varied in the carrier is its amplitude. I stole the slide from our phase modulation, so ignore that phase inversion over there. But what you're seeing is the amplitude jumping between these two values, 100% and a seventh of that. Okay, so this is normalized. And the duration at which it spends at each of these amplitudes is what represents the information. So you're seeing a 1 represented by half time low, half time high, whereas a 0 is represented by 0.2 seconds low and then 0.8 seconds high. And the bit rate being 1 bit per second means that it takes a whole 60 seconds to get a frame of 1 minute through, a frame that contains 26 bits of no useful information, like marker symbols that are meant for synchronization purposes, and not really very efficient in doing that. And of course, these zeros don't contain any information. So we're not going to go into each field and what it means, but just want to make the point that it takes a whole minute to get the time through, including the date, and it's not necessarily encoded very efficiently. And there's no error correcting coding, so if you get a bit wrong, you're forced to listen to the next frame. And there's no advanced notification of daylight saving time, something that we've added. Now, reception challenges, there are many of those, both active and passive. Here we're seeing better simulation results for the propagation, where the areas marked, highlighted in red, are where the field intensity is above 100 microvolts per meter, which is believed to be sufficient for consumer market devices of the type that you find in that magazine or on my wrist. Actually, probably more the wall clocks, because the watches have a smaller antenna and might maybe require a higher intensity of a field. Problem is, when you consider man-made noise and other factors, those sensitivity figures is not as good. I'm sorry about the colors not being so great here, but what we're seeing here is a very high level of man-made noise that I measured in our office in Dallas, emanating from computers and that kind of equipment. It looks like there's actually a peak in the noise around 60 kilohertz, but that's because the antenna resonates at that frequency, so it has more of a pickup there. But it's 2 orders of magnitude above the level of natural thermal noise. Okay, so all those sensitivity figures are naive in assuming thermal noise when the actual noise levels in home and office environments are this. And this is just a quiet place in Dallas. Think about all the garbage that's produced in New York. And then I shouldn't say that I was born in it. My CEO was born in it. I mean from an electromagnetic point of view, obviously. And this interference, 300 hertz away from our signal, I don't know where that's coming from, but once I brought the antenna close to the window, that picked that up. So the point I'm making is there's a lot of interference, active interference in garbage, and that's definitely posing a challenge. Now there's this signal from the UK, and Peter will be talking about, Peter is from NPL in the UK, and he'll be talking about that station. So what I make, the point that I make on this slide is that this station is on frequency. It's very similar in nature. It speaks the same language. In other words, well, it is English, although they say that it's a different form of English. When you talk to a British guy, they're a little more soft-spoken, as the British are. But the fact that it's the same language really makes it difficult. When I come back from work in the evening, and my kids ask me a question in English, and my wife is shouting me a Hebrew at the same time, that works. Nobody has to repeat what they said. You have 2 different filters operating on each. This doesn't work, and I'll go into detail as to why it doesn't work. So I start by explaining how a common receiver works, a receiver that is sold today in watches and wall clocks. It's an AM receiver that has a crystal filter, 10 hertz of a filter, doesn't help when you're on frequency, right? And then an envelope detector and a mechanism that determines a threshold so as to distinguish between a high level and a low level. And then accordingly, the pulse widths are measured and 1s and 0s are established. So what we're looking at here is the AM signal coming from WWVB, and I go through the steps of the demodulation. Okay, so we have a low and we have a high, with the relationship being 1 to 7, and we're trying to extract this duration. Now this is not shown to scale. You're seeing like 5 cycles of 60 kilohertz. It's just for visual clarity, right? With the carrier frequency being 60,000 hertz and this being on the order of a second, it will look very different. And that's the reason why this envelope detector seems to be slow here. It's just because of the time constants that we chose in our MATLAB simulation. So here you're seeing the next stage, which is envelope detection of that. And then next would be to determine what is high and what is low. So there's a peak detector for the maximum, and there's a bottom detector for the bottom. And then there's a middle. So William, you told me that you built a receiver for WWVB in the 80s, right? I guess you did something like this at the time? So you have to detect what is the high level, what is the low level, what is the middle. And then there's a nonlinear element that does a decision and decides, okay, here's a high level, here's a low level, and you measure the duration. So here's what happens when you have that British signal coming in, and its level is 86% in amplitude, that's 1.3 dB down in power, with respect to WWVB. When you add that signal during the low time, you get a 1. Okay, 0.86 plus a seventh is a 1. 0.86 plus 1 is 1.86. The average between the two sits right there at 1. And so that threshold mechanism will be confused by this. So you'd be measuring a high duration of 0.5 instead of the 0.2 that you're trying to decode. This is a marker. Okay, what we're showing here is a victim marker. The markers in WWVB are 0.2 in duration. And then once that marker is no longer appearing like a 0.2 pulse in duration, the clock or watch is helpless. Here we're seeing the same example with the British signal being out of phase. And it's going to maintain some phase coherence for a while before they drift away from one another. And I'm not talking about drift because of accuracy issues, but because of propagation. Okay, there are quite a few milliseconds between, let's say, Florida and the UK. And so with the propagation slightly varying over time from the ionosphere and all that, the phase relationship will vary. Well, this phase relationship, 180 degrees, is shown to be even worse in that when that signal is 4 times lower, 6 dB lower, that would be 4 times lower, or half in amplitude, it's already enough to corrupt the